We all know Earth has one moon, but if you look at the space immediately surrounding our planet, you'll find a hidden, shifting entourage of tiny rocks constantly buzzing around us. Recently, you might have seen headlines about Earth capturing temporary satellites, like the asteroids 2020 CD3 or 2024 PT5. These are what astronomers call mini-moons. They happen when a small rock wanders into Earth's hill sphere, the region of space where our planar gravity dominates over the sun's. The rock gets caught in a chaotic loop around Earth for a few months before eventually slinging back out into deep space. Then there are quasi-moons. A quasi-moon orbits the sun, but it shares our exact orbital path. It paces Earth so closely that from our perspective, it looks like it is circling us. Determining the actual composition of these objects has forced researchers to look beyond the orbital math. Some of these temporary moons are identified as human trash, defunct rocket boosters from the 1960s drifting back into our gravity. But specific natural objects, like the quasi-moon Kamo'oalewa and the mini-moon 2024 PT5, do not match the physical profile of any asteroid we have ever cataloged. Curious, this graph shows a spectrographic data comparison, which measures the unique wavelengths of light reflecting off an object. The light reflecting off these new mini-moons stands in sharp contrast to typical carbon-rich space rocks. Their signature is highly reddened. These rocks defy the standard models of the inner solar system. They are too strange to be asteroids, and they certainly are not human debris. To find a match for this reddened spectra, researchers had to look at samples much closer to home. And if you want to keep exploring these cosmic mysteries with us, take a second to subscribe to the channel. The anomalous light spectra of these mini-moons is a near-perfect alignment with space-weathered lunar soil. This match is supported by modern in-situ data gathered directly from the lunar surface by rovers like U-1 and 2. The evidence suggests that Earth is systematically recapturing lost fragments of its own moon. For heavy lunar bedrock to end up in a sun-centered orbit, it first has to overcome the moon's gravity. Millions of years ago, a massive asteroid slammed into the lunar surface. The kinetic force of that strike blasted rocky ejecta outward into space, with enough power to achieve escape velocity. Orbital simulations and mineral mapping point to a specific geological origin, the 53-mile-wide Tycho crater. These fragments were ejected completely out of the Earth-Moon gravitational system, orbiting the sun for eons before eventually crossing our path again. Earth's gravity is effectively sweeping up the ancient debris of a specific cataclysmic lunar trauma. These mini-moons are highly accessible time capsules of the moon's violent geological past. This chart compares the delta V, or total energy, required for different space missions. Landing on the moon's rugged surface is incredibly energy-intensive. It is significantly easier to intercept a rock that is already traveling in a co-orbital path with Earth. China's upcoming Tianwen-2 mission is designed to exploit this. The spacecraft will visit the quasi-moon Kamo'oalewa, collect physical samples, and blast into the surface to study its interior composition. Earth's neighborhood is surprisingly crowded. Beyond these rocks, researchers have tentatively confirmed ghost moons, eerie clouds of dust trapped at Lagrange points, where the gravity of the sun and Earth reach equilibrium. The next time you look up at the night sky, remember that the moon is not a solitary satellite. It is surrounded by an entire ecosystem of its own fragments, momentarily dancing with Earth before returning to the void.